この番組はご覧のスポンサーの提供でお送りします。
In this video, we are going to show that the hypergeometric probability function approaches the binomial in the limit as big N approaches infinity and p equals r over big N remains constant. A little review. Big N is the number of elements contained in the population. These elements possess one of two characteristics: R, which is the number of successes in the population, and N minus R. Small n is the number of elements randomly selected from the population. And Y here is a random variable of interest, or the number of successes in the sample. Before we proceed to the proof, it is assumed that you know the combination formula and have knowledge about the binomial probability distribution. With that in mind, we know that this R over big N here is the success probability of the hypergeometric probability function, and this P here is the success probability of the binomial. So basically, this is saying that if N is large enough, we can use the binomial probability function to approximate the value of the hypergeometric probability. Finally, we are ready to go to the proof and see why this is true.
Now, where to begin?
First, we write the probability mass function, or the PMF, of the hypergeometric distribution in terms of factorials. In this proof, we will be using x as a random variable because the reporters are more comfortable using this variable. So, we can rewrite this in one line. So now, the next step would be manipulating the right-hand side. Remember that our goal is for our left-hand side to reach the form of the binomial. This one, given that this one. So now, we go back here. In manipulating, we can rearrange the terms like this. May put it here, like that. Or we can also use this to put it somewhere like that, put it like that. There you go. Now, looking at the right-hand side, what do we do? Well, this looks familiar. This, and this. Then we can write this as n, x, and yay, we are one step closer to our goal. Then we have this p here. Know that p is equal to r over big N, and we already have r. We also need the permutation of big N like we have the permutation of r here. We can get this permutation of big N by the big N factorial here. Let's break it down. Rewrite and rearrange. So now, we have this r over big N here. Again, a step closer to our goal. We also join this one and the other one. And whew, it almost looks like a binomial distribution now.
Now, what we're gonna do is we can actually further simplify this equation, and we do it by expanding and see that there are terms or bits that we can cross out. So let's start right here at the numerator, which if we expand, it's gonna be this over this. R minus x minus 1 dot 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 times 1. If you would expand the numerator, we can actually see that we can cross out that bit. So let's now rewrite the whole thing. N just x times r times dot 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 r minus x plus 1, which came from, of course, here. All over. Now what's going to happen with the denominator is that if we can observe, the denominator actually has the same form with the numerator. So whatever process we will do, it's going to be just the same. So it would look like this. There. So here is the numerator and the denominator. There we go. Now let's simplify this other part of this equation. Let's start here and again expand it, and we can actually see that we can cross out this bit. And now let's rewrite the thing we are left with there. And for the denominator, the first thing we should do is rewrite n minus x factorial. Why? So we can see that we can cross out some bits for easier manipulation. So it's going to be n minus n plus n minus x factorial. So if you would expand this thing, it's going to look like this. There. Dot 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 n minus n factorial all over n minus n factorial. We can cross out that bit. So now let's rewrite the thing that we are left with. There we go. So we now have this. Now what we're gonna do here is that we can actually rewrite this and this to product form. So let's first rewrite the whole thing. N just x times, so for the numerator, let's write big pi. Then here, let's write any integer a is equal to that number we will start with, which is equal to 1. And here, we write x. Let's just copy it, r minus x, then any integer a. So for the denominator, let's write b is equal to, again, 1. And it's gonna end when b is equal to x. Then we copy it and minus x plus b. And as we can observe here, for the numerator and the denominator, we can actually see that it both ends with x and it both starts with 1. So we can just write it as 1. We can just write a single big pi and then rewrite k as the integer. Here we go. And now for this side, we write another big pi. Let's write c is equal to 1 since it started with 1 and it's gonna end when c is equal to n minus x. And let's just copy it. And for the denominator, we write again big pi again, then d is equal to 1, and here again n minus x. Then just copy it, and as you can see, both of them ended with n minus x and started with the integer with 1. It's the same. And again, let's just write them both as 1, big pi, and then the any integer is m. And now, there we go.
We are now nearing the end of our proof. Taking the limit as big N approaches infinity, we have this one. We know that we have fixed values for r over big N, small n, and x. So as n approaches infinity, we can ignore these values here because they will become smaller and smaller as n approaches infinity. So we are left with r over n, which we already know is equal to p. Here, we are left with n minus r over n, which is just 1 minus r over n, so 1 minus p. So we can simplify the product notation to this one, which is just equal to the binomial probability function. Thus, we have proven true the hypergeometric probability function approaches the binomial in the limit as big N approaches infinity and p equals r over big N remains constant.
Hi, thank you for watching. I hope you learned something today, and I hope you're doing very well. So stay safe. Bye.